All right, so let's try naming those compounds in question 7.1. It just says provide a systematic name for each compound. So that means they're not going to be based off of alkyl groups. We're just going to find the longest carbon chain and name the substituents, give the first substituent the lowest possible number, and assign stereochemistry if it is relevant. All right, so for the first one, our parent for this one is 1, 2, 3, 4, 5, 6 carbons. So this is some kind of cyclohexane. Now we do have to use locants because there's more than one substituent. And so this would be a 1 bromo and a 1 methyl. We put the bromo first because B comes before M in the alphabet. And so this would be 1 bromo, 1 methyl cyclohexane. Methyl cyclohexane. Like that. The next one, we have to determine the stereochemistry, but remember, I told you that the longer the carbon chain, the higher the priority. So we can actually do this one pretty quickly. The chlorine is going to be number 1, the butyl group will be 2, the propyl group will be 3, and the ethyl group will be 4, and it's in the back. So we go 1, 2, 3. It's clockwise. So therefore, this is an R stereocenter. So the compound is an R compound. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons in the longest chain. So this is some kind of octane. So we have a 4-chloro and a 4-ethyl. The chloro will come first because C comes before E in the alphabet. So this would be R 4-chloro 4-ethyl octane. Ethyl octane. And the last one, did anybody get the stereochemistry in the last one? Is it R or S? Yeah, exactly. It's an R compound, right? You have 1, 2, and 3. The proton is in the back. So yes, this is definitely an R compound. Can't argue with that. So we want to give the first substituent the lowest possible number. So let me ask you guys a question. Should I start numbering by the carbon in yellow or the carbon in green? And again, it's not a trick question. By the one in green, exactly, because a 2, 2, 5 is going to be a 2, 5, 5. Exactly. So I'll start numbering by the carbon in green. So I'll put here 1, 2, 3, 4, 5, 6. So we have a 5-fluoro 2,2 dimethylhexane. So this is R 5-fluoro 2,2 dimethylhexane. All right, there we go. So we named all those. All right, let's turn our attention to substitution reactions. And you're going to have to follow along pretty closely in this one, okay? You have to follow along closely with substitution reactions. Now, the mechanism is not overly complex, but there's a lot of moving parts to substitution reactions because we're going to talk about the nucleophile and the substrate as well in detail. So a substitution reaction requires the loss of a leaving group and a nucleophilic attack. Okay, so substitution requires nucleophilic attack and loss of leaving group. Okay, both of those things have to happen. However, there's two possibilities. They can happen in a concerted fashion or they can happen in a stepwise fashion. Concerted means that both curved arrows are drawn at the same time. So in a concerted process, you would have nucleophilic attack and loss of leaving group occurring simultaneously, whereas in a stepwise version, you would have you would have loss of leaving group, then nucleophilic attack, okay? One would happen, then the other one would happen after, whereas in concerted, it means they happen at the exact same time. So for the concerted mechanism, it involves the breaking of the bond to the new leaving group and making the bond to the nucleophile at the same time. So we have our nucleophilic attack, and our loss of leaving group, but they are occurring simultaneously. You see we have two curved arrows here. So you can take a look at this substrate or our starting material. You recognize this as a primary alkyl halide, right? This is our alpha carbon. It is attached to one carbon. So primary alkyl halide, the nucleophile attacks the alpha carbon, and the leaving group leaves, and we've substituted the halogen for the nucleophile. And of course, we have our halogen. And of course, this would either be chloride, bromide, or iodide. It also could be a tosylate or whatever. But anyhow, there you go. So that's a concerted mechanism. Again, concerted means they're both happening at the same time, the nucleophilic attack and the loss of leaving group. If we have a stepwise mechanism, the leaving group is going to leave first, and then we form a carbocation, which undergoes a nucleophilic attack. So take a look at this. You notice there's a big difference. In the one where the mechanism was concerted, we had a primary alkyl halide. Now we have a tertiary alkyl halide. First, the leaving group is leaving. You form your carbocation, and then the carbocation is susceptible to nucleophilic attack, so the nucleophile comes in. But again, overall, what did we do? We substituted the halogen for our nucleophile. So we're going to look at this particular mechanism, the stepwise mechanism. We're going to cover this in more detail in section 7.8. So that's going to be a little ways away. All right, but let's review. In the concerted mechanism, concerted means they happen at the same time, okay? Sometimes my students will say it's an SN2 reaction. They'll say it's SN together. Okay, both things happen at the same time. And when we have a concerted mechanism, a stepwise, this is like an SN1, and it's like SN1 at a time. That means first the loss of leaving group happens, and then the nucleophilic attack happens second. So to answer your question, is the loss of leaving group always the first step? Yes, because if it doesn't happen, then you can't have a carbocation for the nucleophile to attack. All right. If the nucleophile attacked, right, if it did that and you didn't lose the leaving group, the carbon would have 5 bonds, right, which would be impossible. Okay. Does that help a little bit? I hope so. Okay. So let's take a deeper dive in this whole concerted mechanism thing here. So we call this an SN2 reaction. And I already mentioned this to you. But what does the S, the N, and the 2 represent? Well, the S stands for substitution. Substitution, because it's a substitution reaction, right? You're substituting the X for a nucleophile. What does the N stand for? It stands for nucleophilic. Nucleophilic, because you have a nucleophile that is doing the substitution. And what does 2 stand for? Well, that actually stands for a second order reaction. Second order. Now, this is going back to general chemistry too, when you covered rate laws, okay? If you have a second order reaction, it means the rate is going to be equal to the rate constant multiplied by the concentration of the substrate, okay, multiplied by the concentration of your nucleophile, okay? So it's going to depend on the concentration of the nucleophile and the substrate. And there you go. I've gone ahead and I've written a rate law for this reaction. It says, how would you design a laboratory experiment to confirm the rate law? Well, what you would do is you would say, leave the concentration of the substrate constant, and then you would change the nucleophile, and then you could leave the nucleophile concentration constant, and you would change the concentration of the substrate, right? This is similar to the method of initial rates that you would have seen in general chemistry too. So it says, how does the observed stereochemistry in the following reaction support an SN2 mechanism? So you know that the nucleophilic attack and the loss of leaving group are occurring simultaneously, right? This is a concerted mechanism. So here we have our sulfhydryl ion here, okay? It is our nucleophile and it is attacking. Now, what do you notice is that the stereochemistry is changing from S to R. We're actually inverting the stereocenter. Well, why would that be? The reason why is because the sulfhydryl is not going to attack from the front face of the molecule, right? Because you already have the bromine in the way, and the bromine is delta negative. So the negative charge from this is not going to come close to the bromine. It's going to try to avoid the bromine in order to get to the delta plus of the carbon. And so it's going to attack from the back, okay, the back side of the molecule. And this is not a joke. We call this backside attack. When the nucleophile attacks from the back of the molecule, so then the leaving group leaves simultaneously, and what happens is that it flips like an umbrella in the wind. It inverts. So the stereochemistry here flips from S to R. So again, concerted mechanism, and it's proven by the fact that when the nucleophile attacks, that the leaving group has to leave at the exact same time. So this whole idea of backside attack, okay, so it says the nucleophile attacks from the backside. Okay, there's a couple of ways that you can look at this. The first way is what I showed you on the previous slide. So it says electron density repels the attacking nucleophile from the front side. So that's what I was trying to show you here. You have the electron density on the bromide. So the sulfhydryl is not going to want to attack here, right? Because it has to get really close to that partial negative charge. And like charges repel each other, so it's going to go to the backside. There is a molecular orbital treatment that you can look at here that involves highest occupied molecular orbitals and lowest unoccupied molecular orbitals, which are HOMOs and LUMOs, respectively. I'm not going to test you on that at all. Okay, so what I have the little yellow line by, you're not going to be asked about this whatsoever. So for our class, all we're going to be concerned with is this. We're just going to say electron density is going to repel the nucleophile from coming into the front side. So what's the conclusion? When we do an SN2 reaction, we get backside attack. All right. And so it says here to draw a transition state for the following reaction. This is the reaction that was on our slides, what, 2 slides ago. This concerted mechanism where we have our nucleophilic attack and our loss of leaving group occurring simultaneously, right? You see, we have the nucleophilic attack and the loss of leaving group in this substitution reaction. Well, I'll just tell you the truth. I never ask my students to draw transition states. I don't make students do that. However, it's not a bad idea to see it done and to try it a couple of times yourself. In fact, if you go in the suggested practice problems, I think I even picked one where it says draw a transition state. Look, I'm even posting this on the internet that I said, you don't have to do it, but it's a fun thing to try. It's a good idea to take a look at it at least once because it helps you understand, right? Why does this happen? So if you notice, you started with the R stereochemistry, and then it gets flipped to the S stereochemistry. So what's happening is the methyl, the hydrogen, and the ethyl, you see how they're on the left-hand side, but then after the nucleophilic attack, they're on the right-hand side over here. So we use this is called the double dagger. That's the symbol that we use for a transition state. And what our transition state is going to look like is going to look something like this. So I'll put the carbon, I'll use black. We have the carbon here. We're going to have our methyl group, put it like this. We're going to have our hydrogen like this, and we're going to have our ethyl group going down like this. And then we're going to have a partial bond to the sulfhydryl, okay? And then we're going to have a partial bond to the bromine like this. So this is going to be partially negative. This is going to be partially negative, and the carbon is going to be partially positive in that transition state. So this dashed line here represents bond being formed, and this dashed line represents bond being broken. All right, and that was a lot of work for nothing. All right, so after all that, let me try and redraw it again. So we have our carbon, we have our methyl group up here, we have our proton in the back, we have our ethyl group like this. We have a partial bond to the sulfhydryl, with a partial bond that is being broken to the bromide, and then of course the carbon is delta positive. If you can see that, delta positive, like that. So that's our transition state. And again, I don't make my students draw transition states, but it's a good idea to understand where it comes from. So now it says, draw the product for each of the following SN2 reactions. Well, there's only one here, and it's a reaction with S2-chloropentane and this sodium thiolate here. So NaSH. So we have an ionic compound. So if we have the cation, which is a spectator, and then we have the sulfhydryl ion here, right? This is going to be our nucleophile, right? This is a good nucleophile. How do we know that? It's got a negative charge. So of course it's seeking a nucleus. And then if we draw S2-chloropentane, we'll draw S2-chloropentane like this. So I always draw it with a dash first, and then I evaluate it. So 1, 2, 3. So yes, this what I had drawn is the S compound. So this is the correct compound. And now I'm going to react it with the sulfhydryl ion. So here's my nucleophile. Remember, the alpha carbon is going to be the electrophile. That's this carbon here, right? Because there's a dipole going this way towards the chlorine. That means the alpha carbon is partially positive, so it is susceptible to nucleophilic attack. So I'm going to draw nucleophilic attack and loss of leaving group. How do I know they're occurring simultaneously? They told me that this is an SN2 reaction. So we get nucleophilic attack and loss of leaving group at same time. They gave us the answer, okay? So what do we also know is that the S stereocenter is going to flip to becoming an R stereocenter. So we're going to end up with our 5-carbon chain, but now our S, our dash, is going to be flipped to a wedge. And we've got our thiol on here, and then we have our chloride as our leaving group, like that. Give me a thumbs up if you follow me on this reaction. And that we get the inversion of the stereocenter in an SN2. Okay, so in an SN2 reaction, SN2 reaction, I'll just put SN2, okay? We get loss of leaving group, do it this way. We get nucleophilic attack and loss of leaving group simultaneously. And we also get inversion of configuration. Inversion of configuration. So that would mean R goes to S, or S would be flipped to an R. So if you have a wedge, you flip it to a dash. If you have a dash, you flip it to a wedge, okay? So that's an SN2 reaction. All right, so in this particular case, they told us it was an SN2 reaction, but you're going to get to a point where you're able to look at a molecule and say, oh, an SN2 is what's going to occur with this molecule. So let's get into that and see if we're able to, find a way to make some predictions as to whether an SN2 reaction is going to occur and how fast is that reaction going to occur. So less sterically hindered electrophiles are more readily react more readily under SN2 conditions. Tertiary alkyl halides are too hindered to react via an SN2 mechanism. Now, why would that be? We see that methyl halides and primary alkyl halides are the most reactive. Tertiary alkyl halides don't work at all, really. They're completely unreactive. And SN2 on a secondary, that actually doesn't work all that well, okay? Well, let's think about that. If I have a methyl group, CH3, okay, if I have a CH3, and then I have, well, that's not a very good drawing, but let's say I have, let's try to make it a little prettier. I'll use a finer tip. So there you go. If I have CH3, Cl, okay, so that's methyl chloride, right? My nucleophile, let's say you have the sulfhydryl ion again, okay? It's going to be very easy for the nucleophile to come in and attack, okay? Because protons are so small that they're not going to cause any steric hindrance whatsoever, okay? So this is going to work really, really well. So that's why methyls are so reactive. However, if you replace all of those hydrogens with CH3 groups, let's say you replace this with a CH3, a CH3, a CH3. Well, now it went from going to be a methyl to being a tertiary alkyl halide. And the thing is, it's hard to tell from the picture, right, that I've drawn here, but you have to understand that these methyl groups are really, really big. You've got a carbon and 3 hydrogens. And so the sulfhydryl ion cannot attack. Okay, it can't get in there. It's like it can't even do it. It's like, hello, can I get in here? No, you cannot. It's too sterically hindered. And so alkyl halides that are less sterically hindered, so less sterically hindered, The best ones are going to be methyl and primaries. Those are going to work really, really well under SN2 conditions. Whereas a tertiary, it doesn't work at all. And then a secondary alkyl halide is actually somewhere in the no man's land. It does give you some SN2, but it's not that great. Okay, it's not the best choice of substrate. So let's take a, if you're like, well, can you prove that? Let's take a look at some data here. So this is just a substitution reaction, just an SN2 of an alkyl bromide with an iodide ion, right? Iodide is a good nucleophile. It's negative. Bromide is a good leaving group. It's the conjugate base of HBr, which is a strong acid. So let's take a look at just this side of the chart here, okay? So we go from a methyl alkyl halide to a primary to a secondary to a tertiary, okay? So if you're not following, I'll scribble it in here. Okay, this is a methyl alkyl halide. This one is primary. This one is secondary. This one is tertiary. Look at the relative rate of this SN2 reaction. Again, this is an SN2 reaction. You see it right here. With the methyl, it's really fast. It has a relative rate of 145 times faster than the primary alkyl halide. You can see the secondary alkyl halide, it works to some extent, but it's pretty crummy. Okay, it's a really slow rate. And then if you look at tertiary, it doesn't happen at all. Okay, it doesn't even happen. Okay, so that's when we're looking at methyl, primary, secondary, and tertiary alkyl halides, and we're talking about SN2 reactions. Now, this part here is really important. Okay, it's not easy, but it shows you why a good understanding of concepts in organic chemistry will beat out memorization any day of the week. Okay, let me explain. If you look at all four of these substrates here, all four of these alkyl halides, they're all primary. I can prove it to you. Look, this alpha carbon is attached to one carbon. 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 So these are all primary. But you see that we start adding substituents at the beta position. Okay, so you can't call these primary, secondary, and tertiary, right? They're all primary. But you see that as you start adding substituents at the beta position, you have a whole bunch here in this compound, and the rate of the reaction is just super slow to the point where it's like practically useless. Okay, so that tells you that it's not just based off of methyl primary, secondary, and tertiary. The beta substitution also has an effect as well. So that's why you can't just memorize a rule and just close your eyes and say, okay, every primary alkyl halide is going to work well. Okay, well, no. If you have three substituents at the beta position, the reaction it looks kind of useless to me. Okay, the rate is so slow. Okay, so if we take a look at a reaction coordinate diagram of what's happening, and this is the reaction between, this is just methyl bromide plus cyanide, okay, gives you, this compound is called acetonitrile plus the bromide ion. Okay, so again, this is an SN2, right? This is a methyl, right? Methyl bromide, that's your electrophile. Cyanide is your nucleophile. And you take a look at the activation energy here. Okay, you see the transition state is similar to what I drew a few slides ago. Okay, something like that. It says, what feature is relevant to the rate of the reaction? Well, the part that's relevant to the rate of the reaction is going to be the activation energy, right? That's relevant to the rate of the reaction. But what's relevant to the thermodynamics of the reaction? That's going to be the relative energies. So energies of starting material and product. Okay, so you can see that the product has less potential energy than the reactant, and so this would be an exergonic reaction or a exothermic reaction, either way you look at it. Okay, so there you go. So thermodynamically, this is a favored reaction, and you would look at the activation energy if you were talking about the rate of the reaction. So which one is going to have the fastest rate? Well, here we have a methyl, here we have a primary, and here we have a secondary. You see that based off of steric hindrance, as you go from the methyl to the primary to the secondary, what happens, right? As you go this way, you would say activation energy increases. It gets higher and higher until when you get to a tertiary alkyl halide, it doesn't even react, okay? It's too slow to measure. It's just totally useless, okay? So it's pointless to do that. So what's our take-home message? if you put a methyl or a primary alkyl halide in the presence of a good nucleophile, you're going to get an SN2 reaction. If you do it with a secondary, it's going to work, but the activation energy is going to be really high. Okay, so it's going to be very, very slow. So going back to this idea of neopentyl bromide, I didn't ask you to memorize the name of neopentyl bromide. Neopentyl bromide is this compound. Okay, I showed it to you a couple of slides ago. It's this guy here. Did I draw the structure correctly? I don't think yeah, I did. Neopentyl bromide, yeah, I drew it correctly. Okay, so our alpha carbon, we look at our alpha carbon is attached to one carbon. So neopentyl bromide is a primary alkyl halide. Okay, so you might be tempted to say, yeah, it's going to work in an SN2. But it says here, is neopentyl bromide primary, secondary, or tertiary? Well, like I just said, it's primary. Okay, should neopentyl bromide react by an SN2 quickly or slowly? It reacts very slowly. Okay, and the reason why is because you have 3 substituents at the beta position. Okay, so again, the idea is this. You can't just memorize your way through the whole thing, right? Because all of these are primary. Some of them work okay, or work well. Some of them work okay. But the last one with neopentyl bromide is terrible. Okay, it doesn't work really at all. Okay, it's a very crummy reaction. And so his point for putting it in here is just to kind of tell you, you can't memorize your way through the whole thing. All right, so I would just kind of maybe, I'll put a star by this, put a star by neopentyl bromide, and I'll tell you as my students, I'll just say, make sure you understand neopentyl bromide. If you're wondering, do I have to know a whole plethora of compounds that are substituted at the beta position that don't work well in SN2? I'd say just neopentyl bromide. This compound here is probably the only one that's ever going to show up. Okay, so don't stress about always going to ask me something that I've never seen. Okay, all right, so now that we've covered the electrophile, right? We talked about methyl and primary are really good electrophiles for an SN2. Secondary, it's okay. And then if you get to a tertiary, it doesn't work well at all. Same thing with neopentyl. That is a primary alkyl halide, but again, there's too much substitution at the beta position. So what about our nucleophile? Okay, if you go back to section 6.7, that's where I introduced the idea of a nucleus lover or a nucleophile, something that's going to be attracted to a nucleus, which is positively charged. Well, what are, again, some of the factors that contribute to the strength of a nucleophile? Well, you can see here that if I take methyl iodide as my substrate and I react it with a hydroxide ion, you see the reaction is very fast. Whereas if I take it and I treat it with water, it does do a substitution, but the reaction is very, very slow. So why would that be? Well, if a nucleophile is a nucleus lover, it stands to reason that something that has a negative charge, this has a negative charge, whereas water is neutral, that whichever has the negative charge is going to react faster, right? It's going to find that nucleus faster and it's going to react more quickly. And so generally speaking, strong nucleophiles have a negative charge. In fact, if you look carefully, you'll see that everything here, the iodide, the bromide, the chloride, the sulfhydryl ion, this is called a thiolate. So the thiolate, the hydroxide, the alkoxide, and the cyanide, what do they all have in common? They all have negative charges. And what do the weak nucleophiles have in common? They have no charge, right? They're all neutral. Okay, so these are neutral, whether it's water or an alcohol. Okay, those are both considered nucleophiles, but they're definitely not strong. Now it says here, in general, anions are strong nucleophiles, but also it says here that polarizable atoms are good nucleophiles. So when we're talking about polarizability, remember that polarizability is kind of like the squishiness of the atom. It's its ability to store its electron cloud. And so the bigger the atom, the more polarizable it is. So let's say you were to compare H2S versus H2O. Well, H2S is actually going to be a stronger nucleophile. Why? Because sulfur is bigger, and so it's more polarizable. So we're going to write here, we'll put stronger nucleophile. Okay, they can both behave as nucleophiles, but the H2S, the hydrogen sulfide, is going to be a better nucleophile than the water. Also, solvent affects nucleophilicity. We don't go into a lot of details on this. I would just say polar aprotic solvents are going to promote SN2 reactions. If you're looking at that and saying, I know what polar means, but I don't know what aprotic means. Aprotic means just incapable of hydrogen bonding. And I have that on a slide coming up, so don't worry about it too much yet. All right, so that brings us to E2 reaction. So we've covered SN2. So what was our conclusion with SN2? SN2s work best with a methyl or a primary alkyl halide. They can work with a secondary. Tertiary doesn't even happen. And then we said your nucleophile, well, if it's got a negative charge, that's a strong nucleophile, so that's going to work well. And then we said that water and alcohols, those are nucleophilic, but they're weak nucleophiles. All right. So moving on to E2 reactions, it says that when an alkyl halide is treated with a strong base, it can undergo a beta elimination, which we also call a 1,2 elimination. So you guys know what an alpha carbon is, right? The alpha carbon is the one attached directly to the carbon with the halogen on it. And so its next door neighbor is a beta carbon. So this is a beta, this is a beta. But for instructional purposes, they're just highlighting this one beta carbon here. And so in our elimination reaction, what's going to happen is the base comes along. Oops, wrong place. The base comes along and takes the proton. We make the double bond, and then we lose the leaving group. And so in E2 reaction, remember, it's elimination. It's E together, right? So in this case, it's going to be a proton transfer and a loss of leaving group that are occurring simultaneously, right? You see we're transferring this proton and we're losing this leaving group, and we're also forming that pi bond. So a strong base will react in a concerted mechanism that we call an E2 elimination, right? Both arrows are drawn, or all three arrows in this case, are drawn at the exact same time. So remember, E2 is so E is elimination, but the 2 is not really standing for together. It stands for second order, okay? So if you had to write a rate law, what you would say is the rate is equal to the rate constant multiplied by the concentration of alkyl halide, or this is again just your substrate or your starting material, multiplied by the concentration of the base. And so what are the differences and similarities between E2 and SN2? The similarities is they're both second order. Okay? What are the differences is that an E2 uses a base and an SN2 uses a nucleophile. All right, they both use substrates, so that's also a similarity, alkyl halides. But when we talk about a reagent like sodium hydroxide, which is a strong nucleophile and a strong base, okay? If we have, this is a tertiary substrate, right? This is your alpha carbon, 1, 2, 3 carbons. I already taught you that substitution is impossible because this is too sterically hindered, so we don't get any substitution. But it turns out that if you put a strong base in the presence of that tertiary alkyl halide, you can get a reaction, except it's not going to be a substitution, it's going to be an elimination. Why? Because each one of these methyl groups has 1, 2, 3 protons. And the base, even though it can't find its way into the carbon, it can't go in here because it's too sterically hindered. It can pluck off one of the protons that's on the periphery, right? The protons are sticking out from these carbons, so that hydroxide ion can just go and pluck off one of those protons, okay? And then after we remove the proton, we form a double bond and we lose our leaving group. And so in this case, you would end up with this compound, which we call isobutylene. So when the substrate is sterically hindered, E2 elimination is going to occur. And so to repeat, if you take a strong nucleophile, which is also a strong base, and put it in the presence of a tertiary alkyl halide, it's not that there's no reaction. It's just that there's not going to be any substitution. You're only going to get elimination in that particular case. So let's take a look at question 7.9. It says the following reaction exhibits a second order rate equation. So what happens to the concentration of the cyclopentane if the concentration of the chlorocyclopentane is triple? and the concentration of sodium hydroxide remains the same. So it's telling us that this is a second order rate equation. So what does that mean? It means that we would say the rate of the reaction is equal to the rate constant multiplied by the concentration of the substrate and the concentration of the base. Okay, there we go. So in A, it says what happens if the concentration of the chlorocyclopentane is tripled and the concentration of the sodium hydroxide remains the same. So let's imagine that the rate constant is 1, the concentration of the chlorocyclopentane is 1, and the concentration of the base is 1. Then you'd end up with a rate of 1. But in A, it says what happens if the concentration of the chlorocyclopentane is tripled and the sodium hydroxide remains the same. That means you'd end up with rate of 1 for your rate constant times 3 for your chlorocyclopentane times 1 for your sodium hydroxide. And again, these are just numbers I'm making up, but you'd end up with a threefold increase in the reaction rate. So we'll put here threefold increase in rate, like that. In B, it says what happens if the concentration of the chlorocyclopentane remains the same and the concentration of the sodium hydroxide is doubled. Then you'd have rate is equal to 1 times 2, which would give you 2, which would be a twofold increase. Twofold increase in rate. And then in the last one in C, it says what happens to the rate when the concentration of chlorocyclopentane is doubled and sodium hydroxide is tripled. You'd have rate is equal to 1 times 2 times 3. That's going to give you 6. So that would be a 6-fold increase in rate. All right. So again, second order. It means it's going to be first order with respect to the substrate and first order with respect to the base. Okay. So there we go. All right. Now, you could also practice the mechanism of this reaction if you wanted to. Okay, I'll just rewrite it down here. Here's our chlorocyclopentane. We treat it with sodium hydroxide. And then if we want to make the alkene, what we're going to have to do is, maybe I'll put a double bond over here. There's my black pen. There we go. So what we're going to do is we're going to pull off this proton. So we're going to yank off that proton. We're going to make a double bond and lose the leaving group like that. There you go. So in this case, you'd also end up with water, just the conjugate acid of sodium hydroxide, and the chloride ion like that. All right, let's cover a couple more sections here. Sorry, just looking ahead, just to be sure where I was. So let's just talk about alkenes for a few minutes, and then we'll take another break. But you guys know the difference between trans, right, and cis. You can see it at the bottom of the slide here. We have a trans 2-butene, and then we have cis 2-butene. When it comes to alkenes, because we're going to do some elimination reactions here and make a bunch of alkenes, so you need to know a few things about alkenes. Generally speaking, cis isomers are going to be less stable than trans, okay, generally speaking. And you can see why. It's because you have the two groups close to each other, and that causes steric strain. In the trans isomer, we don't see that. Okay, keep in mind that these are diastereomers. So diastereomers. Anyhow, it turns out that you can actually see a difference in the relative energies of the trans 2-butene and the cis 2-butene. So this is the trans, this is the cis. And you can see the trans actually releases a little less heat, okay, 4 kilojoules per mole less. And so what does that tell you? It tells you that it's more stable to begin with, okay? So it releases less energy when you burn it. So organic chemists learn all kinds of things about molecules by burning them. So the take-home message here, we'll put is trans is more stable, like that. All right. You know, some people need a graph for everything. So here we have enthalpy, and you can see that when the trans is burned, it releases less energy than the cis, which releases more energy because you end up with the exact same product. So the only difference is the amount of energy released. So that tells us that the trans is more stable than the cis. Now, what else? When it comes to alkene stability, it's not just trans versus cis. So we just talked about trans versus cis, but alkene stability is also based on the number of alkyl groups attached to your carbon-carbon pi bond by hyperconjugation. So if your pi bond only has one substituent, one alkyl group, it's called monosubstituted. If it has two alkyl groups, it's called disubstituted. It could be drawn the way that it's shown here, where your two groups could be, they could be cis to each other. Come on, pen. They could be cis to each other. Either one is fine. For tri-substituted means you've got, if you look at your two carbons in the double bond, they're attached to 1, 2, 3 carbons overall, and then tetrasubstituted. So the idea is that stability is increasing going this way. And so the more substitution you have, the more stable it becomes. And the less substitution, the less stable it comes. Okay, and if you're like, where does the stability come from? It comes from hyperconjugation. Okay, that's where the stabilization comes from. So let's call this one A, we'll call this one B, and call this one C. It's not a trick question. Could anybody tell me which one of these is the most stable? Would it be A, B, or C? Remember, look at the substitution on the pi bond. Yeah, A is going to be the most stable, right? So A is the most stable because it's tetra substituted. Which one's going to be the least stable? Exactly. B is going to be the least stable. Why? Because it's disubstituted, right? And then C is tri-substituted, so it's going to be somewhere in the middle. So A is the most stable, B is the least stable, and C is tri-substituted, like that. Okay, so going back to the whole idea of making an alkene, can you have an alkene in a ring? The answer is yes. Okay, but you know, as far as calling the alkene in a ring, cis or trans, for the rings that we look at in this class, it's kind of irrelevant because if you have cyclopropene, cyclobutene, cyclopentene, and cyclohexene, the double bond has to be cis anyway. It can't be any other way. You can try to make a model and try to make it trans, and it can't. I'm going to skip Brett's rule because it's not that important to us in this class. So I'm just going to skip Brett's rule. You can read it if you want. It talks about double bonds near bridgehead carbons, but we're not really going to worry about them in this class. And so what we're going to do now is we're going to take a break before we get into covering the idea of Zaitsev and Hoffman products from elimination reactions. All right.